Welcome back to Weapon Science. I am Ethan Walker. Today, we are dissecting a terrifying reality. Humanity is practically blind to high speed kinetic asteroid threats, relying on an archaic, overloaded communication network that cannot protect us. But a revolution is quietly unfolding in the deep void of space. For over 60 years, every single planetary image, telemetry ping, and astronaut transmission has traveled across the cosmos via radio waves. But this invisible infrastructure is dying. It is too slow, incredibly vulnerable to interference, and completely incapable of handling the data-heavy future of interstellar colonization. To save our future, NASA is deploying something straight out of science fiction: an interplanetary fiber optic network without the actual fibers. By shooting tightly focused, invisible, near-infrared lasers across millions of miles, they are preparing to blast high-definition data through the solar system at the speed of light. But before we look at how we communicate, we must look at how we survive. High-speed kinetic asteroids travel at velocities exceeding 40,000 miles per hour. At this speed, an object the size of a football stadium carries the destructive energy of multiple thermonuclear warheads. Why can't NASA easily stop them? The answer lies in the physics of detection. Current optical telescopes struggle to spot dark, carbonaceous chondrite asteroids against the black backdrop of space until they are dangerously close, leaving us with zero time to calculate intercept trajectories. Kinetic deflection missions, like NASA's DART, require absolute precision. If we miscalculate the asteroid's mass or internal structure by even a fraction, a kinetic impactor might not deflect the threat, but instead shatter it into a shotgun blast of radioactive debris heading straight for Earth. Compounding this danger is our communication lag. When tracking a fast-moving threat, transmitting massive orbital tracking files over traditional radio frequencies takes hours. In a planetary defense scenario, a delay of minutes could mean the difference between survival and total extinction. This bottleneck is caused by the Deep Space Network, or DSN. Composed of giant antenna arrays in California, Spain, and Australia, the DSN is the sole lifeline for every interplanetary mission. Today, it is completely saturated, leaving critical science data waiting in line for days. The fundamental flaw of radio communication is physics. Radio waves operate at low frequencies and long wavelengths. As they travel through space, they obey the inverse square law, spreading out across millions of miles and losing their power density exponentially. By the time a radio signal from Mars reaches Earth, it is incredibly weak, billions of times fainter than the battery of a digital watch. Ground stations must use chilled, ultra-sensitive receivers just to separate this tiny whisper of data from the background noise of the universe. This is where the physics of photons changes everything. Near-infrared light has a wavelength thousands of times shorter than radio waves. Shorter wavelengths mean we can pack vastly more data packets into the exact same physical space, revolutionizing data transmission capacity. Because laser beams are highly coherent, they do not spread out like radio waves. A laser beam sent from Mars remains incredibly tight, concentrating its energy onto a small, highly defined area on Earth, allowing for maximum signal reception with much smaller receivers. We are talking about a bandwidth explosion. While traditional deep space radio links top out at a few megabits per second, laser communication systems can easily achieve hundreds of megabits and eventually gigabits, enabling real-time high-definition video streaming from deep space. This is no longer theoretical. In late 2023, NASA launched the Psyche spacecraft to explore a metallic asteroid. Tucked away on this spacecraft is the Deep Space Optical Communications, or DSOC, experiment designed to test laser communications across deep space. From a distance of 16 million kilometers, 40 times farther than the moon, DSOC successfully beamed a laser signal back to Earth. The data transmission rate was so high it exceeded most home internet connections, proving that the era of deep space laser internet has arrived. To demonstrate this capability, NASA streamed an ultra-high-definition video of a cat named Taters chasing a laser pointer. The video was transmitted from 19 million miles away, arriving on Earth in just over 100 seconds, perfectly preserved and without a single dropped frame. But achieving this requires solving one of the most intense engineering challenges in human history: the pointing problem. Because a laser beam is so narrow, aiming it from a moving spacecraft to a moving Earth is like trying to hit a moving dime from a mile away. At millions of miles away, the speed of light becomes a factor. By the time the laser beam travels from the spacecraft to Earth, Earth has already moved thousands of miles in its orbit. The spacecraft must aim not where Earth is, but where it will be when the photons arrive. Even the tiniest vibration from a spacecraft's reaction wheels can throw the laser off target by thousands of miles. To counter this, NASA uses state-of-the-art magnetic isolation systems that float the laser transceiver, shielding it from any physical disturbance. Once the laser reaches Earth, it faces its final boss, our atmosphere. Clouds, water vapor, and air turbulence can scatter and distort the laser photons, turning a crisp, high-speed data stream into a useless smear of light. To bypass this, NASA uses adaptive optics. Ground-based telescopes measure atmospheric distortion in real time and use deformable mirrors, which warp their surface thousands of times per second to instantly correct the incoming laser beam and restore the data. If clouds are too thick, NASA uses ground station diversity. By linking multiple observatories across arid, cloud-free regions like California, Arizona, and Hawaii, the network can instantly reroute the laser signal to whichever ground station has a clear view of the sky. This is the foundation of the interplanetary internet. Instead of relying solely on direct-to-Earth links, future deep space missions will utilize high-altitude laser relay satellites positioned at stable orbital points, known as Lagrange points, ensuring continuous coverage. This laser backbone will allow orbital habitats, surface rovers, and deep space explorers to instantly share massive scientific datasets, high-resolution maps, and medical telemetry, binding humanity's off-world outposts to Earth like never before. But as we expand our presence in the cosmos, survival requires more than just high-speed communication. It requires food. On multi-year interstellar missions, carrying tons of packaged food is physically impossible due to weight limits. We must synthesize it from scratch. Enter the physics of deep space food synthesis. NASA scientists are developing systems that bypass agriculture entirely by utilizing carbon dioxide exhaled by astronauts, water extracted from life support, and electricity. They can feed specialized microbes. This process, known as gas fermentation, uses hydrogen oxidizing bacteria. These microbes consume hydrogen gas, carbon dioxide, and nitrogen to rapidly produce a nutrient-rich biomass that is extremely high in proteins, essential amino acids, and healthy fats. The resulting biomass is harvested, dried, and processed into a versatile, edible paste. Using advanced 3D food printers, astronauts can customize the texture, flavor, and nutritional profile of this paste, turning raw microbial protein into familiar meals. This is a closed-loop system of absolute thermodynamic efficiency. By recycling waste carbon and water with minimal electrical input, a spacecraft can sustain a crew indefinitely, breaking our reliance on Earth's agricultural biosphere. But food is more than just raw calories. It is a vital psychological anchor. Eating bland paste for years would break a crew's morale. Therefore, these synthesis systems must incorporate biosynthetic flavors and colors to mimic the sensory experience of eating fresh terrestrial food. Furthermore, these engineered microbes can be genetically optimized to produce high levels of antioxidants and radioprotective compounds, actively helping to repair astronaut DNA damaged by cosmic radiation during deep space transit. The engineering challenge is keeping these microbial cultures stable over decades. In cosmic environments, high-energy particles can cause unwanted mutations in the bacteria, risking the sudden collapse of the food synthesis system or the production of toxic compounds. To prevent this, automated genetic sequencing systems constantly scan the bioreactors. If any genetic drift is detected, the system instantly neutralizes the compromised culture and reseeds the bioreactor from a shielded cryogenic seed bank. This technology will face its ultimate test on the first manned missions to the outer solar system. But while we dream of cold, distant worlds, we must also confront the opposite extreme, the hellish, hyper-pressurized, incinerating surface of our sister planet Venus. Venus is a planetary furnace. Every lander we have ever sent there has melted, corroded, and died in less than 2 hours. To understand why, we have to look at the brutal physics of the Venusian atmosphere, which acts like a giant pressure cooker. At the surface of Venus, the atmospheric pressure is 90 times that of Earth, equivalent to being 3,000 feet underwater. Under this extreme pressure, the carbon dioxide atmosphere becomes a supercritical fluid, possessing the density of a liquid and the flow of a gas. This supercritical fluid is highly corrosive. Combined with clouds of concentrated sulfuric acid, it aggressively attacks a spacecraft's metallic seals and structural joints, dissolving protective coatings and compromising internal components within minutes. But the primary killer is thermal runaway. The surface temperature of Venus is an incredible 475 degrees Celsius, hot enough to melt lead. Traditional electronics rely on silicon, which loses its semiconducting properties at these extreme temperatures. At high temperatures, the electrons in silicon gain too much thermal energy and escape their atomic orbits, flowing freely across the chip. This destroys the delicate logic gates, causing the lander's computer to suffer a catastrophic, irreversible system crash. To survive this hell, NASA is developing electronics based on silicon carbide. Silicon carbide is a wide bandgap semiconductor that can withstand extreme heat, pressure, and radiation, allowing sensors to operate directly in the Venusian environment without bulky cooling systems. NASA has even explored building mechanical computers for Venus. By using high-strength alloys to construct gears, levers, and physical logic gates, they can build a lander that does not use electricity at all, making it completely immune to thermal runaway. For thermal protection, next-generation Venus landers will utilize phase-change materials. These substances absorb immense amounts of heat as they melt, acting as a thermal buffer to keep the sensitive science payload cool for several hours longer than previous missions. Even if we solve the heat and chemistry, we must survive the wind. Although wind speeds at the surface of Venus are slow, the density of the atmosphere is so high that even a gentle breeze carries the physical force of a slow-moving ocean current, threatening to tip landers over. Every precious second a Venus lander survives, it must beam its data up to an orbiter before it is crushed. Without high-speed, reliable communications, the immense engineering effort to land on Venus is wasted, bringing us back to the critical need for advanced optical links. But atmospheric challenges are not unique to Venus. Right here on Earth, we face a major barrier in high-speed flight, the sonic boom. And NASA's attempt to solve this with the X-59 supersonic aircraft has run into a bizarre, critical visual engineering hurdle. The X-59 QSST is designed to fly faster than sound without producing a loud, window-shattering sonic boom. To achieve this, the aircraft features an extremely long, pointed nose that prevents shockwaves from merging into a single, loud double boom. But this revolutionary aerodynamic design created a serious problem. The cockpit has no forward-facing windshield. If you put a traditional glass canopy on the X-59, it would disrupt the airflow, creating the very sonic boom NASA is trying to eliminate. To solve this, NASA created the E-External Vision System, or XVS. This technology replaces the front window with a high-definition 4K camera mounted on the aircraft's nose, which feeds real-time video directly to a custom display inside the cockpit. But flying a supersonic aircraft using a screen introduces a deadly risk: latency. When flying at Mach 1.4, a delay of even a few milliseconds between what the camera sees and what the pilot sees on the screen can lead to a catastrophic navigation error. If the XVS system fails, the pilot is flying blind. There is no backup optical window. If the camera lens gets iced over, covered in bugs, or suffers an electrical failure, the pilot has no physical way to see what is already in front of them. To prevent this, NASA integrated multispectral cameras that can see through fog, rain, and darkness, combined with a synthetic vision system that overlays a 3D digital model of the terrain based on GPS data, ensuring the pilot always knows their exact position. The X-59 push for aerodynamic perfection shows how thin the margin for error is in high-speed flight. But when we transition from supersonic flight to orbital re-entry, the stakes are raised exponentially and the physical forces become outright terrifying. This is the domain of SpaceX's Starship. When Starship re-enters Earth's atmosphere at 27,000 kilometers per hour, it must survive temperatures exceeding 1,400 degrees Celsius generated by the compression of air in front of the vehicle. To prevent Starship from disintegrating, SpaceX covered the entire windward side of the vehicle with over 18,000 hexagonal silica tiles. These tiles are made of highly refined glass fibers, which are incredibly lightweight and highly resistant to thermal transfer. Why are the tiles hexagonal? Unlike square tiles, hexagons have no continuous straight lines of gap. This prevents high-energy plasma from finding a straight path between the tiles to reach and melt Starship's stainless steel hull underneath. These silica tiles can be heated to red-hot temperatures and touched with a bare hand just seconds later. Their thermal conductivity is so low that heat cannot easily penetrate the tile, protecting Starship's structural steel skin from melting. But the tiles do not work alone, they rely on boundary layer dynamics. As Starship descends at a high angle of attack, a cushion of cooler, slower moving air forms directly above the tile's surface, keeping the superheated plasma flow at a safe distance. The weak point is how these tiles are mounted. SpaceX uses metal pins welded directly to the steel hull. If a single tile shakes loose during launch or re-entry, the exposed steel hull will face direct plasma contact, risking a localized burn-through. This is where Starship's stainless steel construction becomes a lifesaver. Unlike the Space Shuttle's aluminum hull, which melts at 600 degrees Celsius, Starship's steel hull can withstand up to 800 degrees before losing its structural integrity. During this intense re-entry, the superheated plasma creates an ionized shield around the vehicle, completely blocking traditional radio communications. This is the dreaded plasma blackout, leaving mission control in complete silence for several minutes. But SpaceX solved this. By mounting a Starlink terminal on the top of Starship, where the plasma shield is thinnest, they can beam laser signals up to Starlink satellites in orbit, maintaining real-time video and telemetry throughout the entire re-entry process. This level of integration is what makes SpaceX a dominant force, but Starship's true power comes from its propulsion system, the Raptor engine. To understand its dominance, we must explore the chemistry of the methane revolution. For decades, traditional rocket science relied on liquid hydrogen and liquid oxygen. Hydrogen is incredibly efficient, but it is a pain to work with. It is highly diffusive, leaks through the smallest gaps, and must be stored at extremely cold temperatures. Kerosene, used in the Falcon 9, is dense and easy to store, but it suffers from coking. When kerosene burns, it leaves behind thick black carbon deposits that clog the engine's internal cooling channels, making rapid engine reuse nearly impossible. Liquid methane, or methalox, is the golden middle. It is highly efficient, dense enough to keep fuel tanks relatively small, and burns incredibly clean, leaving zero carbon residue inside the engine, which is key for rapid aircraft-like reusability. The Raptor engine utilizes a full-flow staged combustion cycle. In this design, all the fuel and all the oxidizer are pre-burned in separate pre-burners before entering the main combustion chamber, maximizing the engine's power output and efficiency. This cycle allows Raptor to achieve a mind-boggling chamber pressure of over 350 atmospheres. This extreme pressure produces incredible thrust-to-weight ratios, allowing Starship to carry massive payloads into orbit. But the real genius of methane is that it can be manufactured on Mars. By using the Saboteur process, future explorers can combine Martian carbon dioxide with water ice harvested from the soil to produce methane and oxygen fuel for the return trip to Earth. This chemical reaction requires high temperatures and a nickel catalyst. By converting Martian resources into rocket fuel, SpaceX eliminates the need to carry heavy return fuel from Earth, dramatically reducing the cost and scale of interplanetary missions. This orbital transport capability is not just for deep space exploration, it has massive, immediate national security applications. And SpaceX is already leveraging this with a classified project that is changing global surveillance forever. Starshield. Starshield is SpaceX's military-focused satellite constellation. Built on Starlink technology, Starshield is designed to provide real-time, high-resolution global surveillance, secure communications, and tactical tracking for the Department of Defense. The heart of Starshield is its optical inter-satellite links. By exchanging high-speed laser communications between satellites in orbit, Starshield creates a secure mesh network that can route intelligence data around the globe without relying on vulnerable ground stations. This architecture has massive geopolitical implications. With thousands of laser-linked satellites in low Earth orbit, Starshield can provide continuous real-time tracking of military movements, missile launches, and naval fleets anywhere on Earth, day or night. Because the network is so decentralized, it is virtually immune to anti-satellite weapons. If an adversary shoots down one Starshield satellite, the rest of the constellation instantly reroutes the laser communications through neighboring nodes, maintaining full operational capability. Starshield's Earth observation sensors utilize advanced multispectral imaging. This allows the satellites to see through clouds, smoke, and camouflage, providing military commanders with clear, actionable intelligence even in the most challenging weather conditions. This real-time data is piped directly to tactical units on the ground, in the air, or at sea. By bypassing traditional military communication delays, Starshield allows for instant coordination and rapid response times, redefining modern warfare. The deployment of Starshield represents a shift toward laser hegemony in orbit. The nation that controls the fastest, most secure orbital communication network will dominate both the global economy and the theater of war, making traditional radio satellites obsolete. From asteroid defense to planetary landings, deep space food synthesis, and global military surveillance, the common thread is clear. We are building the invisible, high-speed infrastructure that will support humanity's expansion into the cosmos. The era of radio is coming to an end. It served us well during the dawn of the space age, but the future demands more. The future demands light. With NASA's laser internet and SpaceX's orbital networks, we are finally ready to step out of the cosmic dark. If you want to stay ahead of the curve on the cutting-edge technology shaping our world and the cosmos, subscribe to Weapon Science and hit the bell icon. What do you think is the next big leap in space tech? Let us know in the comments below. See you next time.